Sorry. Okay. So I could try and factor this, but it will not work clearly. Okay, so I go to my quadratic equation. And I see x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And then I continue to simplify. What kind of an answer am I going to get here, folks?
Most likely an imaginary.
Yeah, definitely, not most likely, Dave. 4 times 19 is bigger than 36, isn't it? Surely it is. So this is going to be negative. You're going to get imaginary results. Imaginary results. So, do I really, if I'm trying to find the roots of an equation, I would actually write down what those results are. I would write the results down. But I'm not trying to find the roots here. Let's say I'm trying to find the x-intercepts. Do I have to go any further? Because they're imaginary. That means that the one x-intercept of 2 will be on the graph somewhere. Right there. There's the x-intercept. But this is a cubic function. There's a good chance that its curvature looks like this. I just know what cubic functions look like. It probably looks like this. Okay, that's probably this graph right here. It's like, oh. Let's take a pause and see if we can reconnect AirPlay. Now, if we had a cubic function that had more of a loop to it, right? Because some cubic functions look like this. Now, how many roots could you see on this one? 1, 2, all 3. Remember this theorem? It was other useful theorems. This is this. So, you know that, remember, you always get imaginary roots in pairs. So if you get one pair of imaginary roots, instead of having 3 roots, now you have only 1. Because you lose both imaginary roots. Remember, plus or minus. They are complex conjugates. So again, you could have, for a cubic function, you could have all 3 real roots, or you could have a real root and 2 imaginary. That's it. For a 5th degree function, you could have 5 real, or you could have 1 real and 4 imaginary, or you could have 3 real and 2 imaginary. But no matter what, the imaginary ones need to come in pairs. That was one of those other useful theorems in section 8.5. Okay? Don't forget that stuff. So did we get the idea of section 8.5? How we come up with the depressed equation? If I told you one of the factors, if I said, for example, that x minus 4 is a factor of x to the 7th plus 2x squared, blah, 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 what do you do to prove that that's true?
You plug it in and you divide it.
Yeah, you run it through the table. Now, could you come up with the other factors? Sure, if you can keep going through depressed equations over and over again. So if you were given an example for tonight to work on. If x minus 4 is a factor of, and it's not, I don't think it is, but I'm just going to pick random numbers right now. Something like x to the 3rd plus 2x squared minus 4x plus 5. Okay? I would plug in 4 in the table to come up with the depressed equation. Okay? I would plug in a 4 in the table to come up with the depressed equation. The reason I do that is because the depressed equation will not be cubic. What will it be?
Squared.
It'll be x squared or quadratic, right? And then you can use the quadratic formula on it. What if this were x to the 4th, like this? Then I probably need not just one factor, but
3.
how many factors would I need? Factors. I need another factor. So because look, take a look at this expression here. If I run 4 through it, I'm going to get a cubic. That's what you were answering. I'm going to get a cubic, but I can't solve a cubic yet. So maybe I'll give you 2 factors, and you have to do that. You follow what I'm saying? So if I give you 2 factors, if I said if x minus 4 is a factor, and x plus 5 is a factor, then you could run negative 4 through the table. You'll clearly get 0 as a remainder. You come up with the rest of these numbers. Okay, you have a depressed equation. Positive 4, thank you. You'll come up with the depressed equation. Hypothetically speaking, this is not the answer. I'm just trying to go through it. Okay, you might get like, let's say... Okay, say that's the depressed equation you get as a result. Well, you still can't solve that because it's cubic. It's not quadratic. So now you can use the other factor to go further. Make another table with this equation. Plug in a 5 on the outside now. Or negative 5 on the outside. So make another table, put a negative 5 in, and put the depressed equation up top. And now you'll go from a cubic, which was the depressed equation, to a quadratic. So it's an iterative process. Okay. Iterative means you keep doing it over and over until you get down to what you want.
But if that can be factored,
If you can factor this with the cubic, sure, go ahead and factor it. By grouping, yeah. You could possibly factor by grouping. That's a good point.
So you're trying to get what equation?
You really, in the end, want to get down to a quadratic, so you can use the quadratic formula.
And you get down to a quadratic by dividing by
The other factor, the second. When you use the first factor, you go from a quartic, right, fourth degree, to a third degree. Then you put the third degree on top of the new synthetic table and run the other factor through it. And you go from third degree down to second degree, or quadratic. Then you can use the quadratic formula there.
And then would you do like, because this is fractions, would you then, it would be like x minus 4, and then times x plus 5 times whatever you get for the quadratic?
If you could factor it, but I was trying to find the roots here, not the factors. Same difference, though. I said find what the roots are, not the factors.
Right, but if you're doing this for like, to find the asymptotes, all that stuff, then
Sure, but this is not really used for the asymptotes much.
so this isn't, it's not gonna.
It's another.
Not really, no. This is from 8.5.
Well, doesn't that mean that 4 is our root? You gotta repeat it.
No, I put a 0. It's a 0.
If that's a +1, that's not.
It's a +1. Look,
This is a plus 1.
If there was another plus.
here's the remainder right here.
Yeah.
The last one is the remainder, always.
And was the remainder.
No.
No, if there's 2.
There's a number after that, it's a remainder. Go back and look at your notes. You're just having a brain fart. It's after the constant. Okay? No, I'm not making fun. I'm just saying.
When did we do it?
Go back and look at like 8.4. Look at synthetic division.
I remember doing this in like, yeah,
I thought this was on the last test.
yeah.
The beginning of it was the same thing as 8.4. I told you that. The 8.4 section that we looked at for the test had to do with the synthetic table because we did synthetic division. Okay? That's the reason why. You guys got to look back. You got to study the night before. I know there's no problem sets, but that doesn't mean you couldn't have done problems. There was 8.5 and 8.7 problems listed on the problem sets. So if you need to go back and look at this, you really have to do that. We went over a lot of this, spent a lot of time on this stuff. Now, 8.7 was talking about the list of possible roots, always from looking at P's and Q's. So let's pick a random function. Let's say 2x to the third plus 4x squared minus 7x plus 12. What gave us P, what gave us Q in this setup? What gave us P and Q worth?
The coefficient of the first term. I don't know if I got the book right.
Good?
And then the very end, the one we had a variable.
So the leading coefficient and the constant. Okay, leading coefficient and the constant. What are P and Q? They're not 12 and 2. They're much more than just 12 and 2. What does P and what does Q stand for? Dave?
All the factors.
All the factors of each. So list the values of P. And list the values of Q. Why do I put a plus or minus in the front? Why do I put a plus or minus in the front? And anybody should be able to answer this. We're just listing factors. Why do you put plus or minus? What's the reason behind it? Termin.
Because it's
Not cubed.
It's squared, so it's.
No. Listing factors, Georgia.
Well, I was gonna say because it's squared, because you can do, -1 squared is the same as 1 squared.
Okay, that's true, but that's not the reason. When you list factors of something.
Oh, because two negative numbers can multiply to a positive number?
Yeah, so look, see this is negative 12 at the end? It could be 6 times 2, or it could be negative 6 times negative 2. It could be 3 times 4, or negative 3 times negative 4. It doesn't have to be squared. You guys are making a little more, too much for it. Okay? When you factor something, it could always be plus or minus. Always, always, always. Even a number that's negative. Negative 15 could be negative 5 and 3, or 5 and negative 3. So theoretically, whenever you list factors, it's always plus or minus. Now, what we do to list the rational possible roots is write the ratio of P over Q. And we list all the possible values of P over Q. So let's go ahead and do that now. Take the first or the largest value of P, which is 12, and put it over the values of Q. Put it over both of them. Like that. Okay? And then keep going. then do it with 6, then do it with 4. But as you go through this process, simplify. It makes life a whole lot easier. The first one is really just what? And the second one is just 12, obviously, right? Now, I'm going to do 6 over 2. What is that? Do I have to do 6 over 1? Because I've got 6 already. So don't do 6 over 1. Then do 4 over 2, which is just 2. And then 4 over 1 is 4. Then 3 over 2 I need. But do I need 3 over 1? I don't need 3 over 1. So again, what am I doing? Because I see some confused looks. I'm pairing up each value of P with each value of Q. So I paired those up first, right here and right here. Then I went to 6, then I went to 4, then I went to 3. But I don't need to put 3 over 1 because I've already got 6 over 2, which is 3 over 1. Then I go to 2. 2 over 2. Well, that works, right? That's just 1. Do I need 2 over 1 though?
No.
Because that's already here. How about 1 over 2? That's a new one, isn't it? 1/2. Slide this all over a tiny bit so we can get this. Do I need 1 over 1?
Yes.
No. Oh, yeah. We don't have one yet.
Oh, I didn't put 2 over 2. Oops.
It gets confusing if you don't
You can
like.
put 2 over 2 or.
I forgot 2 over 2 actually. Let me just add that in here, right
Or
here.
you can just.
That's where 2 over 2 should have been. See that 2 over 2 right there? Should have been before 2 over 1. Oh, that's why I wrote 2 over 1 instead of 2 over 2. Duh. Just change this. 2 over 2. Okay? So this 2 over 2 is really 1. So we've listed all of the possible roots. Now, why does this help us? Why does this help us at all? It's called the rational root theorem. The rational root theorem.
Because all of the numbers wouldn't work.
Yeah, all of them aren't going to work, but maybe what?
Some.
Maybe some of them will work. So it gives us an idea of where we need to look at our graph or what numbers we should try. And you're going to learn in pre-calc about a method where you could try any of these. And based on the results you get in your synthetic table and the signs being plus or minus and stuff, it tells you whether to move up or down. It's called Descartes' rule of signs. If the signs are alternating or the same in some pattern, you could tell whether the root is above or below what you tested. So if you test like the number 2 and you get a certain pattern out of the plus or minuses in the chart, you know whether it's above 2 or below 2. It's kind of cool to see that. Now, I give you the option at this point, though. I tell you just look at your calculator for now. Okay? You'll learn more about this in pre-calc. And just find out one of the roots. So go ahead. Go ahead, please. And it might not be any of these, by the way. It may not work. There may be no rational root to this. There's always a possibility. But type this in Y1. Type it in Y1. See which root it's closest to. Yogurt.
Yeah, I got a.
It's going to be irrational, so it's not going to be a rational root. That's it. Good.
Yeah.
Let me see.
Wait, everyone else got this and I got this.
No, it's the lead.
I think it's like the.
I pressed zoom 6.
I pressed zoom 6 on the straight line.
It says error, it says error.
Can I see?
I pressed zoom 6 and that happened.
Oh, yeah. And then it shot up.
It says error.
So hit go to. Go down and it'll tell you where it is.
No, I pressed zoom 6 and
Bring it right to where the error is.
Now it's a straight line.
Guys, whenever the calculator says error, don't just hit exit. Go to go to. The second one, not got to, it says go to. It brings you to the error.
I said
Yeah, nobody ever knows that.
It's working, then I put Zoom 6 and that happened.
Zoom 6.
That's right. So, what you'll notice is this. What you'll notice is this, folks. You'll see your graph, and you're only going to see this root here, and then you're going to see something like that, probably. Okay, so if you Zoom 6'd it, I think you only saw it in this blue box I'm showing you here.
It
Okay?
shows like a little tip of the.
This little bottom one. Now,
Mine's really simple.
clearly, this root, okay, this root, these roots or whatever they are going to be imaginary up there that don't show up, right? Let's take a look. Hypothetically speaking, though, what is that closest to? It was around 3 point what? Negative 3 point?
4.
Yeah. That's not really close to any of these, though, right? If we list our roots, we have 6, 12, 3, 2, 4, 1.5, 1, and 0.5, all of which are plus or minus. So what does that tell me? What does that tell me? This is good that it didn't work. I'm happy, actually. What does it tell me about this? We got 4 as one of our possibilities, right? 4 over 1.
Oh, sorry.
What does this tell me? None of these are the roots. So there are no rational roots. No rational roots.
So it's like.
But there are roots though. They're still there. Press calculate, find the zero of the function. You can find the root. It was like 3.49 something. You can find the exact value of it if you wanted. But you have no rational roots in this problem. You have no rational roots in this problem. Yes, sir.
On the test, will there be
There could be always,
Where
right?
does it? Wait, how do you get the? It's saying like I said left bound.
So pick like -7 to the left hand.
Oh, you
Type
have
in
to.
-7.
You have to do that.
Yeah, type in like -7. You don't have to use arrow keys. And then type in like -5 or -1 rather. So it puts back the walls around the root. And then hit enter and guess.
Oh, it's yeah. Okay, because my old math teacher said that you could just.
Yeah, it's negative 3 point.
No, you can't. If there's only one root, technically you can always just press enter. But if you have more than one root though, you definitely cannot.
Yeah, it's
But
negative.
he probably told you only linear functions and stuff.
Doesn't
with
this
these
have
roots.
one root?
So in that case you can, I'm saying, yeah, but in general don't assume that all the time.
Okay.
Because it doesn't work when there's more than one. I know.
Mine had like,
What if you spill that?
It's negative 3.5-ish.
Negative 3.49.
Eight, no, 3.89, 78723, 76597, 575.
Right here, right? It's like -3.5. Any of those numbers are -3.5? Not really. -4 is none of those being impossible. That's what you can tell. It's easier that way. It should be correct. All right, let's say hypothetically for a second that our graph showed that there was an x-intercept at 2. What would I do then? What would be the approach to this process? We're not going to do it, but I'm just going to talk about it, okay? What would I do if the graph showed an x-intercept at x equals 2? What's the process next? Because I want to find, remember, all the roots. Sure, if you see on the graph 2 is a root, that's great, but I want to find all the roots, and the other roots might be imaginary. So how do I find the other roots if I know that x equals 2 is one of the roots to start?
you can do that, like what we did in 5.
Yeah, that's exactly right, and that's why I said to you, they're very similar topics. So Ida, give me the numbers I would run in. What were the numbers along the top? The original equation.
2, 4, -7, 12.
Okay, and I would run 2 through the equation. Hypothetically speaking, had it been a root, what would I get as a remainder? 0. I will definitely get 0 as a remainder if this were a root. It is not a root, we know that, so I'm not going to get 0, but make believe it is for now. Now, as a result of that, I would get a depressed equation, right? I get a number here. Let's see, bring down the 2, 2 times 2 is 4, 8. It's going to be 16 minus 7 is 9, 18. And we make this negative 18, we get 0. Okay, hypothetically speaking, how'd that work? So I'd have 2x squared plus 8x plus 9, set that equal to 0, and then we could use the quadratic formula. You could try and factor that, that's fine if you want to. Okay, but I would use the quadratic formula to make it easier on myself. Does that make sense? Okay, so the rational root theorem, once you can find at least one of the roots, you'll get a depressed equation from it. You need to practice this tonight. You can't just not do this. And make sure you practice. Yeah, the other roots are imaginary, I think. Let me think of something else I wanted to discuss. Anything else in this section? Hypothetically, that'd be the number to give you 0. That's what the equation would have been to give you 0 as a remainder. But then it would have been different P's and Q's, right? So, guys, again, this is not a problem. You want to practice this one, but go to your textbook or look at the review document I put up. That will work out in some fashion or order. Okay?
What is the equation set to plus or minus?
Negative b plus or minus the square root b squared minus 4ac all over 2a. I feel like there was one more thing in this section that I'm forgetting. Bothering me. Oh, yes, there is. A type of question that I think I assigned it last year, but it was in a problem set. It was definitely in one of your homeworks. Okay, so it depends on if you got there or not, so I'm helping you out for those that maybe didn't get through all their homework. If I were to tell you the following, if x minus 3 is a factor of x squared, or x cubed, plus 2x squared minus kx plus 8, what is k? Very difficult question looking at it the first time. Once you do it once, you're like, this is so simple. But you have to come up with the idea of what to do. Think about it for a minute. Think about it for now. I want everybody, even if you know, just think about how you would approach this process to figure out what k is. And sure, trial and error is a method you could always choose, but I would not do that here. So try numbers forever. What can you do to figure out what k is and guarantee that you can find k? Not just by trying random numbers.
Oatmeal?
It's yogurt, we clarified this.
Can you divide?
Well, how? Long divisions with that.
Longer.
Okay, you could do long divisions, get really messy though.
It would, okay.
So I would use.
Oh, synthetic, oh,
Let's do that. All right?
So would you put k?
Exactly. So what goes on the top?
You go 1, 2, negative k, 8,
Very good.
and then whatever is equal, k equals whatever is.
What's on the outside?
8, 3. Where's the 3?
So let's pause, and that's exactly right. Good start. If it's a factor, what must the remainder be?
0.
So put 0 there already.
Oh.
And the question becomes, at a certain point in time, we're going to have something that we need to do some math with to get 0. So we'll figure out what that is. Let's run through it. Do it together, please. Everybody together. Bring down the 1. 3 by 1 is 3, plus 2 is 5. 3 times 5 is 15, minus k is 15 minus k. You see that? It's a variable now in a sense. Again, 3 times 5 is 15, add the next number. So adding a negative k is really minus k. Now you do 3 times the quantity 15 minus k plus 8, and that equals? That's your equation to solve. Okay, let's go through this. So we get, remember, multiply, add, multiply, add, multiply, add. 3 times the quantity 15 minus k is what I would do. Then I would add the 8 to it, and it would become whatever's next. Well, the remainder is 0. Hold on, guys. I know.